Okay, we've got a quick review of the Finding Redox lesson. Uh, First of all, make sure you know these new definitions of oxidation and reduction. Oxidation will always show an increase in oxidation number, and reduction will always show a decrease in oxidation number. And that's for a specific element, the element that's being oxidized or reduced. So it says here one way you can try to find redox is to assign an oxidation number to everything. However, as a good chemist, you should be able to sort of recognize when you're likely to have a change in oxidation number, just so you understand the reactions more, and it makes the problems a little bit easier to do. So there's a few hints here. Number one, if you're showing a half reaction, it will be obvious whether it's an oxidation or reduction, because gain of electrons, meaning they're on the left, means it's a reduction, and the loss of electrons, or when electrons on the right, means it's an oxidation. So that's easy. What's a little bit harder, but still not too hard, is when you're looking at a complete reaction. So if you have a chemical reaction, it either has both oxidation and reduction, or it has neither of them. And the way you're generally going to look for oxidation reduction is to look for a change of species. And this is a word we've probably used before, species, but it's sort of the form that a chemical is in, and it could be an elemental form, either an individual atom or maybe a diatomic molecule, or it could be an ion, or it could be a molecule where it's combined with other elements. And many elements appear in many, many different species. And in general, when the species changes, there's probably a change in oxidation number. So if you look at all these examples for sulfur here, sulfur actually has a couple of elemental forms. You don't need to know about S6 and S8. We usually just write it as S. But in that case, it's not going to matter because the elemental forms always have an oxidation number of 0. And that's always going to be different than the oxidation number in these other species. So you can have a monatomic ion, which again might appear as just an ion or it might appear in a compound, and then polyatomic ions. And if you actually go through and do the work here, you will probably find that sulfur has a different oxidation number in the sulfide ion versus the sulfate ion versus the sulfite ion versus the thiosulfate ion. And then here are a bunch of molecules with sulfur. There are more, but these are representative examples. And again, there's so many examples here that you could probably find a couple of different species that have the same oxidation number. But if I randomly picked any two of these species, they would almost definitely have different oxidation numbers. So if you see one of these on one side of the equation and one of these on the other, then you're going to suspect that sulfur is undergoing oxidation reduction. So here's an example that shows that. Here's sulfur and thiosulfate on this side of the equation, and here's sulfur and sulfur trioxide in this side of the equation. And if you read through the lesson, you'll see that there is a difference in oxidation number. All right. Here's kind of a counterexample where you have sulfur not changing species. In other words, this sulfur is in sulfate as part of sulfuric acid, and this sulfur is sulfate as part of potassium sulfate. So with no change in species, there's no change in oxidation number for sulfur. This is an important note about fluorine, oxygen, and hydrogen because they almost always keep their oxidation number, -1 for fluorine, -2 for oxygen, and +1 for hydrogen. Even the common different species, there's probably not going to be a change in oxidation number. Always be on the lookout for what I'm calling unusual species here. And unusual is basically anything where fluorine is not -1, oxygen is not -2, and hydrogen is not +1. And most commonly, that would be the elemental form of the species, or sorry, of the element. But there's other possibilities as well. When hydrogen bonds to a metal, that's unusual, and hydrogen won't be +1 in that case. And when oxygen bonds to fluorine or to itself, such as in a peroxide, that would also be an exception. Another hint here, transition metals can have a number of different oxidation numbers, so it's good to check transition metals in your equation for redox if you suspect redox. And then finally, there's a guide about different types of reactions. Probably the most important thing in here is a reminder that if something is an element, and it appears as an element in a reaction, it is definitely going to be a redox reaction. because on one side it's an element with oxidation number 0. On the other side, it's combined with something. And when it combines with something with a different electronegativity, there is either a full or partial tendency to gain or lose electrons. So that element will be oxidized or reduced on the other side. All right. So single replacement reactions are going to be always redox because they contain elements. Double replacement reactions, you might remember we did a question in the POGIL at the beginning of the year that showed that we're just swapping the ions, but they're not changing their species. So those are never redox. All right. And read through the rest of the questions here in the lesson about combustion, decomp, and synthesis. So I think that's about it. Quick review of finding redox. You got some problems on the finding redox worksheet. You can do extras for extra practice and let me know if you got any questions.